Hello, my name is Rodrigo, and I'll present our work titled Loop Rolling for Code Size Reduction. We also have the artifact for this paper, and you can find more details in the link above. First, I'll motivate our work using this example extracted from the Linux kernel. In this example, we have 5 function calls, all of them very similar. And our goal in this paper is to exploit these similarities by rolling straight-line code into a loop, reducing code size. In this example, we'll first create a function to contain the rolled loop. Since we have 5 function calls, we create a loop that performs 5 iterations from 0 to 4. Since all these function calls point to the same function, we can create this function call inside the loop. If we look at the first argument of all 5 function calls, the first term is the same in all cases, which is this use of the state variable. So we can just copy this variable to the rolled loop. In the second term of the first argument, we have an addition in all cases except the first one. But we can assume that having no addition is the same as having an addition of 0. And now we have a similar code in all cases. If we look at all these integers, they represent a sequence that goes from 0 to 16, 16 to 32, and so on. If we compare the difference between these adjacent values, we'll see that they have the same difference of 16. So we can represent this addition by a number inside the rolled loop as well, because they follow a specific pattern. So we'll add by the iterator times 16, which can exactly reproduce all elements of this sequence. In the iteration 0, we'll have 0. In the iteration 1, we'll have 16. In iteration 2, we'll have 2 times 16, which is 32, and so on. So we can easily represent the second term of the first argument as well. If we continue to the second argument of the function call, again, we have the same variable being used in all cases. So we can just copy this term to the rolled loop. And the remaining part of the second argument is the index operation of this array. And the indexing operation follows a very easy pattern. It's just an increment by 1, which can easily be represented by the iterator itself that goes from 0 to 4 exactly. So in the rolled loop, we can just index by the iterator. And if we compare these two functions, we can see that the size of the first function in the binary format is 143 bytes. And the size of the second function in the binary format is 115 bytes. This represents a reduction of 20%. This is a great reduction on a real piece of code that can be found in the Linux kernel. Now I'll describe how we can perform this transformation automatically inside the compiler. For this purpose, I'll use an intermediate representation similar to LLVM to represent the source code. So we'll use this code in the intermediate representation to describe our technique. Our technique starts by identifying what we call seed instructions. And these seed instructions can be instructions such as function calls, store instructions, file nodes, return instructions, and so on. And our goal here is to identify similarities that grow from these seed instructions. We look into the SSA graph that arises from these seed instructions. For example, the first seed instruction grows into this SSA graph. The second one can be represented by this graph, and so on. Once we have these seed instructions, our technique tries to produce an alignment graph that represents the similarity that arises from all these seed instructions. So our technique builds an alignment graph in a bottom-up manner. So starting from all call nodes, we have a match and we produce another call node in the alignment graph. And then we look at the corresponding operands in each one of these nodes. If we look at the left operand, they're not the same, so we don't have a straightforward match. But as we have seen before, in the first case, we simply have an offset by 0 that can essentially be represented by the same operation as the other cases. So we'll add a gap instruction as the left operand of this call node that also uses the state variable as its own left operand. And as the right operand has a sequence that goes from 0 to 64, incremented by 16, as we have seen before. On the right side, we have 5 load instructions. So this is a straightforward match. So we can just add this node in the alignment graph. And again, if we look at the operand of this load instruction, we have a similar situation, where in the first case, we have a variable, where in the other cases, we have an offset by a specific value. So we can assume that the first case has an offset of 0. And again, we'll just insert this gap instruction here that uses the st.v variable as the left operand, and as the right operand is the sequence from 0 to 4 incremented by 1. Now that we have this alignment graph, we will produce the rolled loop for this code on the left side. Since we used 5 seed instructions, we'll create a loop structure that performs 5 iterations. So it first has a pre-header that simply jumps to the loop body. In the loop body, we have an iterator that starts with 0, which is then incremented by 1. And then we have a comparison to check if it has reached the limit of the number of iterations, which in our case, the last one is 4. And then we have a conditional jump to either continue the loop or exit the loop. Going to the exit block that simply contains the return instruction in this case. Once we have created this overall structure of the loop, we produce the code for the alignment graph in a top-down manner. If we start by the highlighted node, this node computes the sequence from 0 to 64, always incrementing by 16. So we'll use the iterator to compute each value of this sequence inside the loop simply by multiplying 16. Then we'll produce the gap instruction that uses the state variable and the result of the multiplication as the second operand to compute the offset of the pointer labeled state. On the other side of the graph, we have this sequence that simply goes from 0 to 4, incremented by 1. This is what the iterator is already computing. So we can simply use the iterator in this case. Now we have another gap instruction. In this case, we'll just use the iterator for the offset value. And this gap instruction is used by a load instruction. And then now that we have both operands of the call instruction inside the loop, we can also create the call instruction inside the loop. These 5 instructions represent the code generated for this alignment graph. And this is the whole code of the road loop. And now that we have finished producing the road loop, we can compare both versions to see which one is smaller. In our compiler, we perform a profitability analysis, which uses a cost model. to decide which version produces a smaller code in the final binary. And in this case, we'll realize that this is a reduction and use the road loop version. In addition to the straightforward matching nodes, we have seen that we can handle some special cases. The first special case we have seen is a monotonic integer sequence. In our example, we have seen the sequence that goes from 0 to 64, always incrementing by 16. And we have seen that we can produce the code using the iterator times 16. In the general case, we'll have a sequence, for example, this one that starts with S0, then we have S1 up to Sn. The only restriction that we have is that this sequence must have the same difference between adjacent values. So S1 minus S0 must be the same as S2 minus S1, and so on. If this requirement holds, then we can produce the code inside the loop to represent this sequence. And the general formula would be the first value of this sequence, S0, plus the iterator times the difference between two adjacent values, in this case, S1 and minus S0. We may also have mismatching code in our alignment graph and still be able to produce the road loop. In this example, we have these three values that compose the mismatching node. Since we cannot identify any specific pattern between these constant values, we consider them as being a mismatch. In the general case, when performing code generation for a mismatching node, we'll import the values into the loop via the stack memory. So in the pre-header, before entering the loop, we'll allocate an array in the stack memory. Then we'll store each one of the mismatching values into this array in the pre-header. So in this case, we're storing 5, and then we're storing 1, and then we're storing 0 into this array. And then inside the loop, we'll use the iterator to index this array. And then inside the loop, we'll use the iterator to index this array and load the appropriate value depending on which iteration we are running. And then the loaded value will be used in the computation inside the loop. If we have only constant values, we can actually create a global array of constants and simply index that global array and load each one of the values directly from the global array without creating an extra stack array and storing each value individually. This produces a smaller code with a smaller overhead, but only works for sequence of constant values. Another special case that we can handle are the reduction trees. This example, we have a dot product, which is a very common example. In the case of the reduction trees, we have a single seed instruction. For example, this return instruction at the bottom. And then from the seed instruction, we collect the reduction tree, which consists of adjacent nodes performing the same reduction operation. In this case, we have these two addition operations being performed. And if we look at the frontier of this reduction tree, we'll have the new seed instructions that we'll consider for the construction of the alignment graph. So our alignment graph will have this return instruction. We have a special node representing the reduction tree. In this case, the operation of the reduction is the addition. And then from the new seed instructions, we'll grow the alignment graph on top of the reduction. For the code generation, the reduction node will produce two instructions. First, we have a find node that starts with the neutral element of the reduction operation. In the case of the addition, the neutral element is 0. And then we have a second instruction that actually performs the reduction operation itself, which feeds back into the phi node. The remaining of the alignment graph goes in between these two instructions, and it computes the value that goes into the reduction operation. In this case, it's this multiplication that feeds into the addition. So in summary, for the code generation, we first create the overall structure of the loop with the pre-header, the loop body, and the exit block. Any preceding code goes into the pre-header or before. Any succeeding code goes into the exit block or afterwards. All the matching nodes and the special nodes go into the loop body. All the mismatching nodes, we first allocate a stack in the pre-header. We store all the values in the pre-header basic block, and we have a load operation inside the loop. We may also have external uses, which values from the alignment graph being used outside the alignment graph. In this case, we also need to create an array in the stack with values being stored inside the loop and being loaded outside the loop in the exit block to be used externally. So while for the mismatching nodes, we have multiple stores in the pre-header and a single load in the loop. For the external users, we have a single store inside the loop and possibly multiple load operations outside the loop in the exit block. For our evaluation, we implemented our technique in LLVM, which we're calling roll-lag, and we compared to the existing loop re-rolling technique that exists in LLVM. We explained the loop re-rolling technique from LLVM in our paper in the background section, but in summary, it only works on loops that already exist and has been partially enrolled, and it works on a top-down manner, starting from the loop iterator, and then it finds the increments of the loop iterator, and then identifies the exact pieces of code that represent each one of the enrolled iterations. And all these pieces of code must be the same. Unlike this technique, our technique works on a bottom-up manner, and it identifies similarities in any straight line code. The first benchmark that we evaluated is the Anger bench, which contains a collection of real code extracted from popular GitHub repositories, such as the Linux kernel, the Postgres database, and so on. We measured the reduction of our technique over OS, which is shown in this graph. We're not including the loop re-rolling technique from LLVM because it only affects less than 50 functions, so it wouldn't be visible in this graph. And overall, our technique achieves very good code size reduction, in some cases reducing the size of the function by over 8%. In some cases, we have some code degradation. This degradation is due to the profitability analysis, misjudging the size of the final code in the binary format. This is a result of inaccuracies of the cost model that we use. But overall, we achieve a significant code size reduction across these functions. We also evaluated on full programs, and these programs were extracted from the MuBench and Specs 17 benchmark suite. The LLVM re-rolling technique, once again, has very limited impact in these benchmarks. And our technique is able to find significant reduction opportunities, in some cases reducing the binary of the whole program by around 2.5%, which is the case of the POVRE benchmark, and in other cases reducing by small amounts. We also have some code degradation, but overall have an average positive code size reduction. Finally, we evaluate our technique on the TSVC benchmark, which contains several kernels of specific loops. This is ideal for the LLVM loop rerolling technique because you can partially unroll these loops by hand and just stress these two techniques to see where they fail and where they can successfully reroll the partially unrolled loop. And in this case, the LLVM technique is able to achieve positive gains in several of these kernels. But our technique is able to cover all these cases and many others. And the reason for this difference in code size reduction between LLVM and our technique is because we don't reuse the structure of the outer loop when we are rolling straight line code. So we simply create an inner loop inside the existing outer loop. So we can improve code size reduction by reusing the structure of the outer loop and just changing the increments of the iteration of the iterator and the loop bounds. And this is what the LLVM technique is doing. But this can be easily improved in future versions. Thank you for watching my talk. For more information, look at our paper in the link above. And if you have any questions, please let me know.